So the real just returns the cosine part, the imaginary returns the sine part. One of the keys that we're going to do though is converting this to Euler form, because Euler form is going to allow us to use exponent rules to combine them. Okay, that is one of the biggest keys to this entire unit.
When combining.
Mhm. So you'll get something like this. So it says, write it in terms of complex polar form. So this is a sine, so that's the imaginary part.
Showing the cosine in the end. See.
And I believe that's exactly what they want.
2x plus 3. I mean, take the derivative of that. The 3 disappeared. Yeah.
Oh, I put it in Euler instead of polar because that's where we want to get to. I just went straight to Euler.
Radius times e to the
What's inside?
angle.
Yeah, the angle, which was 3x plus 1 this time. So let z1 be a plus bi and z2 be c plus di. Show that real z1 plus z2 equals real z1 plus real z2 and imaginary. Okay. So I'm going to do this without converting. I believe I can do that. Z1 is a plus c, right? Plus b plus d I. That's my addition. The real part is real. The real part is just a plus c, right? Which does equal real z1, which is also a plus real z2.
Do that. Yeah, like kind of
So if I'm adding these, I get a plus c, right?
the imaginary. Well, complex though.
Yeah, complex numbers.
Okay, yes.
So the real part of this and the imaginary is going to be the same thing, so it's just a plus c, correct?
Is that just like the notation for like real part of z1 plus z2?
So it's asking me for what is the real part of these two added together. And it says it wants you to prove that it's the same as that. So real z1 equals a. Real z2 equals c. And the imaginary thing would be doing the same thing, but with the b plus d. So real z1 plus real z2 equals a plus c. So now we're going to show it with these. So them being cosines, I'm gonna do a different color now.
How do you take the derivative? It's.
They are the real part.
No, say say.
So, like the sinusoids, they're only one part of the complex number. They're either the real part or the.
A cosine is the real part, and a sine is the imaginary part.
I do it.
They both.
Add.
You're not going to do any that have both?
Perfect.
Uh-huh.
So they're either or.
So this is real 2e to the x plus 1 I. That's my first one.
We're just converting those to.
So we're converting them each to Euler, and then I'm going to put them together and show that it's that. And usually I don't actually go to the intermediate where I have the CIS step.
You go. This one. So,
RE and the IN are just like notation to tell us that it's the real
Really
imaginary.
Yes.
They don't actually change the value of it.
They don't change anything on the inside.
So
It just says that this was not really truly CIS. It was not cosine I sine. It was just cosine.
So it's like, oh, it's like what I did. It's just like telling you it's only the real part.
Yeah. So the beautiful thing about these is I can do the real. So what I've done here, I'm doing two steps at once here. I'm adding the two things and I'm distributing those i's. Does that make sense? So I'm just taking the two things together and then I distributed the i's as I did it. I'm going to write out the next step while you're doing that, and I'll explain when you get done. So what I'm doing, when you add exponents, you multiply with like bases. So this right here
Oh yeah, we
turns into that.
like an expo.
Yeah.
Yeah. I would not have thought of that. So
No, that's
no.
this is why we teach you, because you won't come up with most of this on your own. Don't just hand you a book and say, here, figure it out. I would not have come up with this on my own. Then I saw it and I was like, oh, that's kind of brilliant.
Why do it make sense? One's bottom there in the middle.
And then I factor out an e to the xi, and I end up with what I'm supposed to get.
Well, this is like it's like still in Euler form. This is like the combined Euler form of
Combined Euler form, and then it says put it back to here. No, now it wants it back to cosine. So
So it would be actually I don't know.
um
Because the angle would it be like
Okay, so here's what we're going to do before we put it back to cosine. 2e to the I plus 3e to the pi I.
Those are just numbers.
Those are complex numbers. So this is, actually, I'll go through how to do this by hand, and then I'll show you with the calculator on the next one. So 2e to the pi I, angle here is 2e to the I. Okay. That's, wait, that's 1i. So that's 2
That makes sense.
with an angle of 1. This is 3e to the pi I is 3 over here. There. Because this is like 3 CIS pi.
Are we looking okay. Two. Well,
So these are the,
which one did we draw out?
I've got both of them. This one's there. Maybe I'll just do it in 2 different colors. This is not going to be very nice to add. So blue, here I've got blue. It's a radius of 2 and an angle of 1. Because your form is RE to the theta I.
Oh, and we have one.
Theta is 1. This is 2. No, I should use purple.
And then the next one is 3 and 5.
So the angle is pi, the radius is 3.
Just on.
So this one is simply -3. This other one here is, I'm going to need a calculator for that. So
Yeah, I'm actually not beautiful.
well, why is that?
Because I go home and then I sleep. Or go to work and go there.
Sleep. I'd rather be here than at a job, but sleeping. Makes sense.
Okay, so I'm just going to do cosine and sine to get my, so I am in radian mode. I need to be in a calculator. 2 sine should give me the y coordinate. Cosine should give me the x coordinate. Six, 8.
So we have 1.6.
So my blue one here is 1.08 plus 1.68i. So when I'm adding -3 to that, I get oh, I'm not in polar form. So this becomes -1.92 plus 1.68i. I guess now I need to convert that back to polar. So when I add them, I get,
That's all we did was add them.
yes, negative 1.92, 1.68. So to convert it back to polar, I would two. Two is my radius. That's interesting. My angle, I'm going to do an inverse tangent. Oh, shoot. No, this I screwed up. This is 1.92. 1.68, 1.92. Square root of answer. No. 2.55. That this probably makes more sense. And
We're gonna go inverse.
inverse tangent. Yep. And we'll end up having to do pi minus. Tangent is opposite over adjacent. So I get 2.42. So that comes back here as 2.55 e to the 2.42 I. Does that make sense?
Mm-hmm.
So then to go back, I can multiply these. I've got e to the xi and e to the 2.42i, which when I multiply, I add the exponents, correct? And then I factored out. And so it's 2.55 CIS x plus 2.42 or 2.55 cosine x plus 2.42.
Right.
Check that I'm right here. Yep.
So we've got 2.55 cosine x plus
2.42. That's about the only time you'll do it by hand. But does that make sense how I did that? I just converted it to regular, converted it back. It's a bit of a pain.
Even converting back to signs, it's just the imaginary part. You're still not gonna have an I in your answer because it's not not in polar or
Yeah, it comes back out. This is a little trick of going into polar and Euler form of complex numbers so that we can do some of these rules and then we bring it back to sine or cosine.
because you're like solving the problem as if you had sine and cosine.
Mhm. And you're solving it as if it was polar form of complex numbers, but it isn't actually. Okay, we're gonna do one more, and this time we'll let the calculator do the combining for us. But hey, we got the right answer. I could have done that with a scientific calculator. Prefer not to, but given this, show this. Okay? So essentially, I'm going to have this start R e to the ax plus b1. Oh, why on earth are they doing this? Okay, I know what they're doing.
So we are adding f
Yeah,
of x and g of x.
one of the keys to this is they have to have the same value here as the a. Okay,
What? Where?
so this value has to be the same.
For the addition to work?
Hmm. In order for this to work, essentially the a is in the place of the period modifier, and it has to be the same period. And we'll get to an application tomorrow with voltages, and that period is essentially what's called the phase, or how often does it change direction in alternating current. So these are not quite the same, but here we go. So we're supposed to prove that that equals this.
So what we've done is convert both of them to
To Euler, yeah.
That's basically it.
That's all I've done so far. And put them in the same imaginary thing. Now I'm going to distribute.
So the A's are the same, but the B is different.
The B's are different. Yep.
Is the same.
And this is I. So all I've done so far is distribute the i's. It is still in an imaginary. Now I'm going to break those apart. And I'm at this point just not worrying about this part. So then I can factor out an e to the axi.
Hmm. Oh, Oh, that's why that works, is because the A is always the same.
Mhm. Yeah, that's why it has to be that.
That's why you can't combine them.
This stands for magnitude. So this is a complex number that we can simply,
Take them, find the magnitude.
mhm.
It's because when
So
you
that's magnitude. So this is essentially e to the axi. I guess there's an imaginary out here still. And this is in complex form. CIS. Argument just means angle for that.
so they're just written this one strange thing.
Yeah.
So it's basically what we did on the last problem, just
Mhm.
written really funky.
So, and then you distribute that back in, which puts it as, when I distribute that back in, I get imaginary.
What step did we what did we distribute here?
I distributed this into there.
Why didn't we distribute it into the magnitude? Or did we? And I'm just not.
It's multiplied. So it could essentially be e to the axi. And then the rules of exponents would say this is just all multiplied, so I multiply these, which is add. So that's how it ends up there.
Okay, where did the I go? Because we have AXI, so.
So that's here, right? That's part of the CIS. So your general form is R, which is that. I'll do a lot of colors here. R E to the AX plus theta I. So there's your AX. This is your lovely theta. And they factored out the I. And then you go back to CIS, which, and then you go to sine. As I get rid of the imaginary part. Okay, I'm going to do an example with numbers, and then we're done. So I have these two AC voltage sources. One is 110 volts, the other 80. Do you see how that shows up on this?
Oh, this is like a probably skipped.
Yep. 110 and 80. And we are told that they have this for the waves. You'll be told that. The maximum voltage on this one's 110 because they make like you can represent alternating current with a sine wave, and the voltage is the high and low. So the maximum is the max of the sine. 110 or 80 for V2.
So we have two different waves.
We have two different voltages combining together, two different sine waves. B.
So they're like they're all the same intercepts.
The not necessarily the intercepts because they have a different shift,
Okay.
but they will share the same frequency of their peaks. So to do this, we start by converting him to polar. 110 e to the bt plus pi I plus 80 e to the bt plus pi over 4 I. This makes sense so far? I'll distribute my i's. I will make mine I'll split that. I don't want parentheses here. This makes sense what I've done so far. So I just distributed the I split it up. I'll factor out the e to the b ti. Again, I'm still in the imaginary. Now I'm going to take the calculator and add those, which is brilliant because it can. Erase a couple things over here. This is why it's great to have an Inspire. E to the pi. Okay. Plus 80 e to the pi divided by 4 I. And here it just added them for me, but that's not in complex form, is it? So menu, number, complex number tools, convert to polar. I'm gonna write this out, even though it's a little messy. A calculator. And I did the one by hand, but you can use your calculator for all of these. So now I'm here. these two, I don't really actually need the parentheses anymore. That's just times. So I've got 2e to the power of something I, which means I can just add the exponents. I'll go to 3 sig figs now. I can factor out my I. And I can convert it back to sine. My maximum voltage of the two sources is 77.8.
Oh, okay. It's interesting.
They're apparently offset enough that the one is reducing the voltage of the other. So if you're looking at them graphed, it probably looks something like here's pi. I don't know what the period is. The other one would start at, pi over 4, not go as high, but it's in the negatives. It's negative when you got that peak or something like that. So they don't perfectly line up. This is probably not a peak at the bottom. But however this would work, the peaks don't actually line up. And so you've got negatives when positives are happening, etc. Does that kind of make sense how to do that? We will do another one of these tomorrow. But that's basically the gist of it.